This video provides a discussion of how you may assess the normality of a continuous variable. These variables are generally going to be falling at an interval or ratio level of measurement. A common assumption pertaining to continuous variables when carrying out various statistical procedures is that they exhibit normality. Normality of your variable x is a requirement to appropriately utilize the unit normal distribution, also known as the z-distribution, when finding the area under the normal curve. Normality of your variable is assumed when carrying out t-tasks, comparing two groups on a dependent variable. Normality of your x and y variables will provide benefits when carrying out correlation analysis. In fact, your correlation analysis is hindered to the extent that your x and y variables exhibit different distributional shapes. So it's important to note that no variable will exhibit perfect normality. Normality or perfect normality would be considered an ideal rather than an absolute state of affairs. Nevertheless, we often evaluate our data for a variable for normality by comparing our variable against that ideal. There are two dimensions of continuous distributions that bear on the assessment of normality. There's skewness, which represents the degree of asymmetry in scores within a distribution, and kurtosis, which represents the relative peakiness to tailedness of a distribution. So here's an example of a distribution, a normal distribution. And so basically a normal distribution exhibits this type of shape. You can see that we're assuming it to be continuous. We're also saying that the distribution is bell-shaped, so it takes on a bell-shaped kind of quality. Has symmetry, meaning that the area under the curve that falls at or below the midpoint of the distribution or median of the distribution is exact, and which also lines up with the mean and mode, is the same area that we have above that point within the distribution. So basically, within a normal distribution, it's bell-shaped, it has symmetry, it's also unimodal. So the height of the curve represents basically it's capturing the relative frequency of scores within particular areas under the curve. So the greatest frequency of scores within a normal distribution are falling in the center of the distribution, and as we move out into the tails, scores on the distribution are becoming less prevalent. So as you can see, as we move out into the lower tail and the upper tail, the proportion of scores that are falling out in these regions is becoming less and less, whereas as we move towards the center of the distribution, the proportion of scores that are falling in at the center is much greater. So the height of the curve is capturing the proportion of scores that are falling in different regions underneath the normal curve. So and with a normal distribution, it's unimodal, meaning that it has a single mode. So you can see that the height is greatest at this point, which is lining up with the mean median mode of this particular distribution. So with a normal distribution, the mean median mode, a perfectly normal distribution, the mean median mode would all fall at exactly the center of the distribution. And that's why, basically we can say then that the area that falls at or below this point is equal to the area that falls at or above. The symmetry is capturing the fact that as we move out from the center of the distribution at points that are equidistant to each other, the area that falls between, say, the center of the distribution and that point is the same on both sides of the midpoint of the distribution. So you can see that between the mean and one standard deviation unit above the mean, that actually encompasses about 34% of the distribution, and the mean and one standard deviation unit below that point would capture another 34%. So the area between -1 and +1 standard deviation units is about 68%. As we move to about 2 standard deviations above and below the mean, that encompasses about 95% of the distribution. And in fact, the area between the mean and 2 standard deviations above would be about 47.5%, and the same percentage would be found between the mean and 2 standard deviations below. And then between the mean and 3 standard deviation units above and below, that would encompass about 99.7% of the distribution. So you can see that the symmetry is what allows us to talk about how much area there is under a curve between any 2 points underneath the curve. So again, we assume then that the normal distribution is bell-shaped, has symmetry, and is unimodal, and basically it will exhibit these properties with respect to the relationship between standard deviation units and the area underneath the curve. Now, as I said before, there are 2 dimensions that bear on the assessment of normality. There's skewness and there's kurtosis. So skewness deals with the issue of asymmetry. And so basically when we have a normal curve is non-skewed. In other words, we have these properties in terms of there's no pileup of scores on one side or the other side of the median in the distribution. So again, with a normal curve, we would have the mean, median, mode actually lining up right in the center of the distribution. If we have a negatively skewed distribution, think about it this way, that along this axis right here, these are the raw scores running from low to high. So there's no pileup except right kind of in the center of the distribution, and you see proportionally fewer scores that are falling out into the tails. With a negatively skewed distribution, you have more of a pileup in the scores in this area of the scale, and you see sort of a trailing off or trickling off of values that are occurring at lower and lower values on your variable. So in this particular distribution, the mode is falling right here. The mean is actually falling up here because it's being pulled by the extreme scores, and the median would fall in between. So you would see then that the mean, median, mode are not lining up in a normal distribution. Whereas when the mean, median, mode sort of separate from each other, then there's evidence that you might have some skewness in your data. It doesn't always work out in exactly the same way, but the general idea is that as the mean, median, mode exhibit different values, then there's more evidence that you would have skew in the data. So in this particular demonstration right here, the mode is falling right here, the mean is falling out here, and the median falls in between. So basically you've got 50% of the distribution that falls right here. That's between the high score and the median, and 50% between the lowest score and the median. And you can see there's much more spread in terms between the lowest and the median, lowest score and the median between these areas, as opposed to between the median and the high score. So in a negatively skewed distribution, the skew is this portion right here, and so in this case, that is our negative skew because it's on the downside, so to speak. With a positively skewed distribution, you can see a reversal of this trend, so that you have a pileup of scores on the lower end of the scale, and you sort of have a trailing off of scores in the upper end of the distribution. So in this particular distribution right here, the mode is falling right here. The mean is falling out here, being pulled by the extreme scores on the upper end, and the median falls in between. So skewness can be assessed using histograms and with skewness statistics. These are things that we can assess using SPSS. We can also ask for statistical tests of related to normality, of which skewness is partly impacting. So we're not going to talk about that just yet, but we're just going to focus on the scale that's conventionally given is this right here. So basically a value of 0 would be consistent with a normal distribution. A positive value would be more evidence of a positive skew. A negative value would be evidence of a negative skew. And as I said before, normality is basically an ideal. So we sort of have to come up with some thresholds for just judging whether or not we have a substantial departure from normality on this dimension. And so one rule of thumb that was given was that if we have values that are greater than 1 or less than -1, that would be more indicative of a substantial skew in the data. So basically, if we have a skewness value or a skewness statistic value that's falling between -1 and +1, then we would deem that, according to this rule of thumb, uh, we would infer that the distribution is reasonably consistent with normality. In terms of kurtosis, kurtosis has to do with the relative peakiness to the tailedness of a distribution. And so oftentimes kurtosis is described as being the peakedness of a distribution, but it's actually comprised of two components. That's the peak and the tails of the distribution. So in terms of kurtosis, we have three types of kurtotic distributions here. Distribution A is basically consistent with what we would expect with a normal distribution. So this would be our ideal in terms of what is normal in shape. And so that distribution is considered to be mesokurtic. In terms of a kurtosis statistic, the kurtosis statistic would have a value of 0. Distribution B that we see right here is called platykurtic, and basically in terms of a kurtosis value, that value would be negative. So you can see that we have thin tails and basically sort of a flat distributional shape. So there's our platykurtic distribution. And then C is a leptokurtic distribution. Basically, it's a distribution with a positive kurtosis value. And you can see that basically we have thicker tails. As we move to the center of the distribution, it becomes more peaked. And then as we move out, thicker tails. So that is the shape of a sort of more of a leptokurtic distribution. So it's a bit trickier to evaluate graphically using histograms, whereas skewness is pretty easy to use histograms or the skewness statistic. Kurtosis is a little trickier with respect to histograms, but we can use the kurtosis statistic, which is centered at 0, and if we have positive values, that would indicate positive kurtosis. Negative values would indicate negative kurtosis. There are various rules of thumb that have been suggested for assessing kurtosis. One rule of thumb that we're going to utilize is printed by discussed by Lomax and Hosvon. Basically, we're going to use the same thresholds that we use with skewness, and that is that values of kurtosis that would fall between -1 and +1 would be more consistent with a normal distribution. Values that are less than -1 or greater than +1 would suggest more substantial departures from normality with respect to kurtosis. So there are a couple of ways that we can request normality evidence for a variable in SPSS. So this is just sort of a set of screenshots. The first way is we can just go to descriptive statistics, frequencies, move our variable over to this box here, to the variables box. Click on statistics. We can ask for the standard indices of central tendency and dispersion. But then we click on skewness and kurtosis over here under distribution. Under charts, we can click on histograms and show normal curve on histogram, and basically this will give us an overlay of what the expected, what the data would follow if it was normal. So when we click on continue and then on OK, then we get, in terms of our output, we have skewness value. In this case, we have a negative 0.065, which is basically a small negative skew. However, it falls between -1 and +1. So in terms of skewness, we're not departing substantially from normality. And with kurtosis, it's also falling between -1 and +1. So although it's slightly platykurtic in shape, it's not departing substantially from normality either. So according to these two dimensions, it appears that our data are reasonably normal with in terms of shape. Here's our histogram of the data, and you can see that this is a normal curve overlay, and it's not perfectly normal by any stretch, but the bars are largely sort of following this general trend. So we might visually say that the data appears to be reasonably normal. It's not perfectly normal by any stretch, but it's following sort of a general, it has sort of a general normality trend. If we want to test statistically for normality, we can go to Analyze Descriptives and to Explore. We'll move our variable over to the dependent list under Statistics. We can click on histogram and under statistics there are some defaults. We can leave that alone. Click on plots and this box will open up. We'll ask for histogram and normal plots with tests. Click on continue and then on OK, and we end up with our skewness and kurtosis values. These are the same values that we had seen previously when we looked at this chart right here, or that table right there. We get a histogram. It does not give us a normal curve overlay, but you can see generally it seems to be sort of roughly following the normal curve, but it's not perfect, again, by any stretch. And then on this page, we have, or this piece of the output, we have significance tests. So this is allowing us, this provides an inferential test for determining whether or not our data are following a normal curve. And so what we do is we look in the sig column. This is in the sig column. This is significance, and basically these are what are called p-values or probability values. And so they're testing whether or not our data are departing substantially from normality. So the common threshold for judging whether our data are, we can assume our data is normal, is if the p-value that's given right here in the sig column is greater than 0.05. If it is greater than 0.05, then for that particular test, then that would suggest then that our data are following normality. So we have two tests, the Kolmogorov-Smirnov and Shapiro-Wilk test, and basically, the Shapiro-Wilk is probably better suited for smaller samples with n's less than 50. And we actually have a fairly small sample in our for our data set. I think our data, we had 25 cases for this particular variable. And you can see that the p-value is 0.726, which is greater than 0.05. So that would suggest then that we have a normal distribution. The Kolmogorov-Smirnov test also is giving us statistical significance, which is allowing us to, again, suggest or infer that our data are reasonably normal in shape.